Good morning, everyone. Good morning, everyone, and thank you for joining. I will ask for next slide and we'll get started. Thank you. So thanks for joining NEEP's Cold Climate Air Source Heat Pump Sizing Tools tutorial. My name is Tara McElhinney. I'm a senior associate on the Technology Market Transformation team here at NEEP, and I'm excited to share with you all the latest and greatest on our sizing tools with Parker Wall. Users can use the sizing tools on our website to select right-sized heat pump systems that match the needs of specific heating loads, and programs can leverage the tool to support contractors in their network in implementing best practices for sizing in cold climates. So this will give you an introduction and a deep dive on that. Next slide, please. A few things to note before we get started. This webinar is being recorded. It'll eventually live on our website for future use. And in NEEP's ongoing effort to improve accessibility, we have enabled closed captioning. And if you wish to disable it, you can do so in the lower right-hand corner of the screen. The slides and recordings will be sent to all attendees after the webinar. And so send it around to your team, anyone who could use it. And we hope that it's going to be useful. So by default, all lines are muted, so please type your questions in the Q&A at any time. It might be particularly helpful in this webinar to add some context around the questions because Parker will be going through a live tutorial. If we don't get to the question immediately, it might be a good refresher to know what it was that you were asking about. And the chat will also be available for comments, discussion, collaboration, and try to make sure that the questions are in the Q&A because that's the easiest place for us to get them and get them answered for you. Quickly, our antitrust statement: participants shall comply with competition law requirements and shall not enter into any discussion, activity, or conduct that may violate any applicable competition law. Next slide, please. I want to take a moment to thank our Allies Network. Next slide. And our wonderful funders. Next slide. And our state partners. All of our partners help us power the work we do, and we want to give a big shout out to all of them for support. Next slide, please. Now I'd like to bring Parker Wall to the screen stage. Parker is a project engineer at TRC Companies, and he has been absolutely key in the creation and continual improvement of our cold climate air source heat pump sizing tools. He knows them like the back of his hand, so he'll be leading us through a tutorial on this webinar today. Thanks for joining, Parker.
Thank you for having me, Tara, and thank you for the wonderful introduction. As Tara said, I and some of my colleagues at TRC have helped with the development of the tool, and I'll be giving a how to use the tool and how to correctly size your equipment today. Before we get into that, I want to go over why is sizing important. Right sizing is important to maximize efficiency, comfort, and value of the heat pump equipment. Undersizing a heat pump may cause it to struggle to keep the space warm in the coldest of days. The energy bills may spike due to electric resistance used to supplement the undersized heat pump, or another gas fuel system may increase greenhouse gas production if your ultimate goal is to actually reduce greenhouse gas production. Oversizing equipment may lead to low load cycling, reduced efficiency, reduced comfort, more wear and tear on the equipment from stopping and starting so frequently, and then poor dehumidification from not having longer run times for dehumidification times that oversized equipment might have. Oversized equipment also can cost more to the customer to initially install and run. So right-sizing the equipment might get, if you're an installer and bidding a job, bidding that right-sized piece of equipment might get you under your competitors and get you an advantage there. Programs that support best practices for sizing can improve customer satisfaction energy savings, customer satisfaction, and energy savings, leading to a wider market adoption. This is something we believe in and have seen that that really is actually the truth. The sizing tool 2.0. So the sizing tool was iterated 1.0, and then this second round of improvements to it, the new and updated features we will go over today are listed here. I'm not going to go through them one by one here, but we will touch on them today in our walkthrough tutorial. The tool helps users select products that are sized to best match the design and annual heating needs of the space. It uses TMY3 weather data for the local weather station. That uses historical weather data to cast a load profile, an annual load profile of what that home and what that specific project sees. In order to collect your actual inputs, you should be doing manual J, or whoever is doing the sizing should be doing a manual J to get the heating and cooling loads of the space. And then the weather data should take that manual J entered loads and cast an overall annual load profile for the home. Right, we're now going to be going into the live tutorial. As Tara said, please ask questions in the Q&A. I'm going to pause my share quickly. And reshare my internet. So this is the NEEP tool, the NEEP cold climate air source heat pump list, advanced sizing for cold climate air source heat pumps tool. This is the homepage. So if you type in this URL right here, air source heat pump ashp.neep.org, we'll land on this page. It'll ask you who you are, and then you'll have the choice of all these inputs that'll help you size your system. So you can go through product type, ducting configuration, brand, HRI, heating capacity at 47 and 5. And then also what is new to this tool is this eligible for federal tax credit, or if you are looking for a piece of equipment that is eligible for a federal tax credit in the North, you can simply check this button and go through the search, and it'll only filter through the pieces of equipment that are eligible for the federal tax credit in the area you have selected, so North or South. You can also do the same for Energy Star certification, cold climate, or just V6.1. What we're going to do today is the advanced search sizing for heating. And I am going to select a piece of equipment that is, or look for a piece of equipment that is going to fit my imaginary project that is located in Poughkeepsie, New York, in the Northeast. So my zip code is 12603. When I enter in my zip code, you notice that this weather station turns from gray to white, and five of the nearest weather stations pop up in accordance to where that zip code is. To the right of each weather station is the heating design temperature. So I'm going to choose Dutchess County, which has a heating design temperature of 8 degrees. If your specific project may be close to this weather station than others, which would create a good weather profile, but maybe you have a house that is in, next to a lake and has a different design temperature than this 8 degrees, then you can adjust this as you see fit. Same with the cooling design temperature as well. Simply click the up and down buttons, or just enter the number you see fit. What I'm going to do today, the house that I'm looking at here, is really just a small 1 bedroom, one bathroom. And the heating design load that I got from my manual J, say, is 12,500. The cooling design load is 6,500. So if I were to click run advanced sizing for heating search right now, I would pop up with an error because I did not enter in enough of these inputs up here to sort out enough pieces of equipment. It would go through all the list in the tool, all of the items entered into the heat pump list, and that's too many for the tool to search through. So what we need to do is enter in some identifying information for maybe what our distributor sells. So what I'm looking for in this specific home is a single zone non-ducted wall placement. You can select whatever fits this home the best, but for my specific project, it's a single zone non-ducted wall placement. And the brand I'm going to be looking at is Bluefin, because that's what's currently available to me in my area. It could be any of the tools and brands listed here. None are better than others from our perspective, but we just use the manufacturer uploaded information to run the tool, run the calculations, and then hopefully you can sort through them and select which is best sized to your system. So under any one of these systems, under any one of these brands and manufacturers, any specific heat pump might be right-sized, it might be undersized, it might be oversized. That's for you to use the tool and figure out what size that piece of equipment actually is. So with that entered up here in our manual J and location info entered down here, I'm going to click Run Advanced Sizing for Heating Search. That should populate a list down here. I currently have this on list view. You can also use grid view and sort through the grid here. If you want to look at any kind of user page, you can simply click view detail from the grid view. I am going to use list view for the ability to sort and filter these. So if I say the new feature that was added is being able to filter these, if I know that my maximum capacity design temperature, I'm going to want it over 9,000 BTUs. It'll sort out everything below 9,000, and I'm going to want it less than 19,000 BTUs. If you enter that in there, it'll come up with anything that comes through here, and you can do that likewise for any of these columns here. So I'm simply going to click these X's here just to get rid of that and go back through what the original search populated. When I'm searching for a piece of equipment, I like to sort by % design load served. You're welcome to sort by any of these here, but that's just what I like to do. I like to sort by % design load served and then take a look at how these pieces of equipment should kind of size up to what my design load is, which is 12,500 heating design load at 8 degrees Fahrenheit. These pieces of equipment range from about 190 to about 57% of the % design load served. The one I'm going to look at first today, let's look at this one up here. So it's not the biggest, it's 164% of our design load. That means it should be able to heat the home at that 8 degrees outside. Great. 164 doesn't sound like a lot. It can't be that oversized. So let's take a look at it. To open up this page, simply click this little paper clip right here, the view the product page, and it should pop up with the product page. At the top here, you can click Save PDF, which will export a PDF that can be used as a submittal or maybe given to the homeowner for their information. For their future reference, it can be attached to the equipment, attached to the installation manual where you put it there. And that way they can have this piece of this information for the life of the unit. You see your product sizing for heating information here. There's click here for additional optional settings, which we will get to at some point. But the overall flow of this page is the graph information, which shows a visualization of the sizing of the piece of equipment. And then you come down here and you see product sizing for heating and product sizing for cooling, which has some information that we will go through today. And then you come a little below that and it becomes the information tables, which has all the information that's uploaded by the manufacturer. It has your ERC or HSPF 1 and 2 if uploaded. And then it has your product basic age or HRI model numbers in those. You scroll down a little lower if this piece of equipment was eligible for a federal tax credit or was Energy Star 6.1 certified, then you have a little green check mark here. We'll go over some pieces of equipment later that might, but it would look like this and be in one of these boxes. So you tell that this one does not have a check mark there, so it is not eligible for these. And then on the right is the performance specs, which this information, these capacities, minimum, maximum, and rated capacities at all these different temperature points are used to populate this graph up here. We will go through this and use this graph on how to analyze an oversized, undersized, and right-sized system today. Taking a look at this piece of equipment right here, I know it was 164% of the design load served. So I have a decent idea that's going to be slightly oversized. You can see that at 8 degrees, our design temperature right here, you can see that this maximum capacity is well over the load line here. So it's going to be able to heat the home at that design temperature without any issues. I'm going to remove that just to make it a little clearer. In the background is the annual load time hours. So this takes the weather data and your entered heating design load, and it calculates out what the annual load hours, BTU per year, that system is going to be at each individual temperature. So at 30 degrees, it's going to have, this amount of annual load hours per year. Using that, you really want this load line to encapsulate the peaks of your annual load hours when it's within that modulating zone. So it's when it's within this yellow area right here, between the heating minimum and the heating maximum capacities. So you want to maximize the amount of time that this load line is within this modulating zone. You can see that the load line here drops below this heating minimum capacity at somewhere around 36 degrees. If you look down here, the minimum capacity threshold is 36 degrees. So that was correctly judged from the graph. At above 36 degrees, this heat pump might be in danger of low load cycling. You can see that also there's an oversizing warning that popped up here. It says this system has percent heating design load greater than 150% and will likely experience moderate to severe oversizing effects. There is a new oversizing warning for heat pumps that are greater than 120%, and then a second warning that for heat pumps that are greater than 150% of the design load. That the 120 to 150% is a little softer language. It says that heat pump might experience oversizing effects, and then the 150 and greater is more hard language that says it will likely experience moderate to severe oversizing effects. If you wonder what those oversizing effects are, you can simply hover on the info button next to view oversizing effects. That will show some of the effects of an oversized heat pump. As you go through the tool and wonder what any of these wonderful data points mean, you can hover over the info buttons on any of them, and it should give definitions for each one. Again, as we look at this graph here, and we see that it is well sized for the heating design load of 8 degrees, it can handle that no problem. We look at that wedge down here, which is the low load cycling wedge, and notice that it is, above 36 degrees, this heat pump's in danger of low load cycling. And that's for heating. So, at all these temperatures above 36 degrees, this heat pump's going to have to click on and off. It doesn't have the minimum capacity small enough to meet the needs of the space without adding too much heat to the space. We can see that this turns red for a smaller wedge. This will turn yellow and then turn green. If this doesn't look, too dangerous to you, if you're looking at this and going, well, that's not too bad, it really encapsulates most of the space. A good tool, a good feature that was added to the tool is the cooling visualization. So the cooling visualization can be added in if you just simply click the cooling info here. And you can see from this, so this heat pump is oversized for heating, yes, 164% as we said. However, it should heat pretty well, and it shouldn't have too much of a low load cycling issue. 36 degrees and above is not great. It's not great, but it's not as bad as the cooling looks. You can see that the cooling is really going to be low load cycling for almost the entire year. It doesn't meet this, the load line doesn't meet the minimum capacity of the system until 93 degrees Fahrenheit. Now, I know that some of this is going to be latent load removal, but because of the temperature of because the sensible heat is what's shown here, really, in order to dehumidify the space, you're going to have to run on really low dehumidification speeds, or the set point of the temperature is going to have to be low, and that space is going to be, once it gets dry, it's going to have to be cool, because this heat pump is going to have to turn off and on, and add a lot of cooling to the space, and it's not going to be able to run for long periods of time, which is how it best wicks moisture from the air. So this is an oversized heat pump. We'll come back to this in a little and address the three together. But this is looking at an oversized heat pump. Yes, it is oversized for heating, but it looks severely oversized for cooling. And not saying that this heat pump is not the right fit for some projects, it's just not the right fit for this project. So I'm going to go back to my list view, and that one was 164% of the percent design load served. I'm going to select one. Let's see, that was way too big. I'm going to select one with one that maybe is, let's go with the smallest one, that's 57.7%. I'm going to click on the view product page, and it's going to pop up with the same product page as we saw before with the new product info. And then we go down to the graph. It has all the same info down here, both as the first one did. But we go down to the graph and we notice some big changes. So we notice this low load cycling zone down here, this little wedge, is now green and it doesn't encapsulate the peak. It's very small. It's at 50 degrees and above. That's great. That's a very small low load cycling zone. This heat pump is well sized from a minimum capacity standpoint of heating. However, we notice that this heat pump has a supplemental heat wedge. So this purple wedge over here is the difference between the heating maximum capacity and the load line. So the heating maximum capacity and the load line for all this area is the supplemental heat needed to bridge the gap between the load of the home and the load of the space and the maximum capacity this heat pump can put out at that temperature. You can see that the annual BTUs covered by supplemental heat are 7.3 megabTUs, and then the hours requiring supplemental heat are 796. If we went back to our other, there were no hours covered by supplemental heat, or at least minimal hours covered by supplemental heat, maybe on these really low, negative degrees, which are rarely seen. So great. So this heat pump does a really good job of potential load cycling. It's going to run really efficiently for a lot of the hours of the year. However, you're going to need that supplemental heat to make the space comfortable at temperatures below the capacity balance point of 24 degrees. So this point right here, where the maximum capacity meets the load line, is called the capacity balance point. And it is a 24 degrees. That's what this tool calculates for you. If you were looking to run a dual fuel system with this heat pump, one thing you can do is you can say, okay, I'm installing this heat pump in this space. I have a high functioning furnace in the background that already exists. It might be 5 years old. It doesn't need replacement. I'm just looking to install a heat pump for cooling, and then add a switchover point at the capacity balance point. So what you can do is you can click here for additional options, and you can hit optional apply compressor lockout temperature, and then enter in that capacity balance point, 24 degrees, and then hit run system sizing. And what that will do is it will essentially turn off your heat pump at that 24 degrees and make sure that and account for that in the calculations that at every temperature below 24 degrees, your backup furnace or your existing furnace is going to be operating at that temperature and below. So the heat pump is going to be operating at 25 degrees and above, and that furnace is going to be operating 24 degrees and below. And that should be reflected in your annual BTUs. You can see that this went up from 7.3 to 9 in the other calculations we have down here. But for today's purposes, I'm not going to be using that. We'll go back to not having a lockout temperature. And as we looked at the oversizing, the oversize for cooling was extremely oversized. So we're going to take a look at this undersized system. And how does it look at cooling? All right, as you can notice here, this low load cycling wedge right here for cooling is extremely low. This undersized heat pump that for heating really does meet the cooling needs of the space. So it meets that 6,500 cooling design load at 88 degrees. It meets that really well. This heat pump, will operate efficiently and should whip moisture from the air way better than the other oversized heat pump does, because it can run at low speeds for a long duration of time, which is when it dehumidifies the space best. So yes, it does need supplemental heating, but it has low load cycling impacts. We'll come back to this system later in an effort to maybe address a system with multiple compressors in it. Maybe for this one bedroom, one bathroom house, if you wanted to put a 2 mini splits, one in the living room and then one in the bedroom, we can build that in the system and see how they interact together. I'm going to pause here and try and answer some questions. So Tara, do you have any questions queued up for us?
Sure. So there are a few questions about how to use this in Canada. Can it access Canadian weather data? And if not, for the zip code, can we just pick the closest state if we're in Canada?
I actually don't believe that I'm not sure if we can access Canadian zip codes.
I
That's a
think
good question. Do you have an answer to that?
I I think the zip codes are based on ASHRAE weather zones, so I don't think they do include Canada.
I
But
think
I
you're
will
right.
say Natural Resources Canada also has a sizing tool that you can input NEEP data to. It's not as seamless because it doesn't capture the data in the site itself, but I'll link it here in case that's useful for you, for anyone. Oh, Jason says he's been using it in Canada, finding the US zip codes closest to the design locations in Canada.
Yeah, that's what I would suggest. And then if we are able to find some weather data for the Canadian weather stations, similar to what we currently have, we can add that in the future iterations of the tool. But I would suggest for now using the closest weather station to where you're located, to try and best represent, the annual profile of that location. And you can adjust the heating design temperatures as necessary to fit whatever is suggested in your area.
Thank you. There's a question about, does this tool assume block loads for the entire building rather than zone loads?
Good question. So it depends on how you enter it. If you are entering in to look your heating design load, that's completely up to you. We suggest that you enter in your heating design load as a whole, look at your whole system, and then look at those individual zones to make sure that the heat pumps to assess how that individual heat pump will affect that individual zone. So if you're entering in your block load, then it's assessing your block load. If you're entering in your room by room load, your zonal loads, then it will do the same thing, but it will assess that zonal load. If you're we'll look at it in a little bit, a new feature that you can add multiple compressors to one system. We suggest it's a great way to look at your overall profile, but we still suggest in that language that you should look at each individual compressor in the area that it will be heating and cooling to make sure that it's sized well for that specific zone.
Great, thank you. And I don't want to take up too much of the time because I think some of these can be answered later as well. But can you speak a little bit to why cooling parts are off the chart by default and whether there's any consideration of removing the rated line showing up as part of the default chart?
Can you say that last part again?
Yeah, is there any consideration of removing the rated line showing up as a default chart?
Good question. I'll address that part first. When I'm looking in a system, I simply almost always just delete the rated line because we all know that what we're looking at here with the sizing actually matters for these variable capacity heat pumps is that minimum and maximum capacities and where they affect the system. The rated line can be useful for some pieces of equipment, but typically I just click on it and get removed from the chart. It makes it a little cleaner to look at. The reason why cooling is not included by default is the Northeast, you should be sizing for heating. We really want to be driving that point home that we do want to size these heat pumps for heating if they're going to be whole home solutions in the Northeast. And then look at the needs for supplemental dehumidification after you assess the heating needs. So the choice was made to leave cooling off for those homes that we want to drive the attention towards the heating, make sure that that looks good, and then address cooling after the fact after you make sure that the home should be comfortable throughout the winter. And then to just add it back in, as anyone here has hopefully seen during this during this tutorial, you can simply just click them and add them back in as needed. So you can adjust what you see in your graph and what's important to you.
Thanks, Parker. I'll let you continue with the tutorial and we'll save the other questions for after the next pause.
Thank you, Tyler.
Thanks.
So now that we've looked at an undersized heat pump and an oversized heat pump, let's try and find one that might fit our project really well. So I'm going to go back to our list view. We still have our search. We entered in a single zone non-ducted wall mount. Our brand is Bluefin. That's what our distributor is selling for the area. And then we have our locational info, our heating design temperatures and our heating design loads, our cooling design temp and our cooling design loads. And we sorted by percent design load served. We look at one that was 164%, and we looked at one that was 57.7%. Let's look at one down here. See, this one is 101.0%, almost perfect to our design load. That looks like it should operate really well. Let's go ahead and select this, hit view for product page. That'll pop up in the system. That is 101% of our design load. And we scroll down here and look at the graph and look at it, and just by a quick assessment, we can tell that it is, 101%. It's right around that design load. The maximum capacity is right around that load line at the design temperature right here. This heat pump does appear to be well sized for that design temperature. And then we look at the potential low load cycling zone. So this one, we remember our oversized heat pump was 30 degrees and above, and our undersized heat pump was 50 degrees and above. This one looks to be about 46 degrees, which is, 46 degrees. Our minimum capacity threshold is that point right there. Our capacity balance point is 8 degrees Fahrenheit, which is coincidentally our heating design temperature, which is a great way to size these pieces of equipment. So this heat pump should have, relatively low amount of hours percent low load cycling, 12.6% annual time spent, or annual load low load cycling. So only 12.6% of that annual heating load is in this little green wedge down here. Percent annual load modulating is 75.5% of the year. 75.5% of this annual load is spent in this modulating zone, which is when this heat pump should be operating most efficiently. To take a quick look at the cooling, let's add those in. And we can see that the cooling, this is a little red orange block here. It is a higher, it's a larger wedge than what the undersized piece of equipment had, but it's not as severe as the oversized piece of equipment. So this cooling minimum capacity threshold is at 83 degrees, which I think our other oversized was at 90 or a little higher even. And that 83 degrees is pretty good. So below this 83 degrees, if it's really humid and high 70s, and you're just trying to cool it down to 72, this heat pump might struggle to run for super long durations of time. But for a lot of the year, it shouldn't have too much of an issue with that, not compared to our oversized piece of equipment. If you're in a really humid area that has a lot of hours of the year at this 75 to 80 that's very humid, you might want to look for supplemental dehumidification or heat pump. If this one has dehumidification mode on it, you might want to run it in dehumidification mode for those lower temperatures and humid days. However, we can tell that this does not need supplemental heating at the design temperature. If you have a lot of hours below that, you might want to add some supplemental heating or maybe strip heating. But for this specific piece of equipment that is ductless, you don't need supplemental heating for this manual J entered load. And then also there's relatively low amount of the year that's going to be spent low load cycling. It may not be as good at the low load cycling as the undersized piece of equipment, but it does fit the design load. So you don't need to add supplemental heating and others as you would in that undersized piece of equipment. And then if you look at the oversized piece of equipment, you obviously don't need to add supplemental heating, but you do have a lot of low load cycling. So that's the trade-offs between undersized and oversized. And this is what a right-sized piece of equipment will typically look like for a heating and cooling design loads as entered here. So I hope you can identify from the graph what an undersized and oversized piece of equipment looks like. We'll go through and actually add some of the new features of the tool and go over those really quickly. I'm going to go back to the list page and add in the pieces of equipment we just looked at. So I'm going to click add this green plus sign here. That's going to add it to this bottom tab here. Now, if you were to do a new search for maybe a piece of Bosch equipment, or maybe a similar brand with ducted configuration and complete a new search, it should keep your piece of equipment down here. So you can compare between manufacturers as you wish. If you maybe have a maybe you have a distributor that sells Mitsubishi and Trane, because they're both similar, they both come from the same company, you might be able to compare those pieces of equipment that your distributor has to see which will best fit your home. But today I'm going to stick with what we've already looked at. I'm going to look in, we've already added the one that we looked at that was 164%. Let's look at 101% down here. Let's add that one in, and then let's look at this 57.7%. Let's add that in. And then you add all three to these. If you add two of one product, the compare products page will go away. To simply remove that, just click the minus sign there, and the compare products will pop back up. I'm going to hit compare products, and it's going to come up with one graph for 3 pieces of equipment. How is that? You can simply click the arrows here to slide back and forth between the pieces of equipment. It'll identify it by your AHRI number. And I hope that you all have enough experience from our quick tutorial on how to identify which piece of equipment is which. You can see that this one has a large low load cycling zone and has a high heating maximum capacity of the design temperature. This is our oversized piece of equipment. This one has a relatively small compared to the other low load cycling zone and is just about right for our design temperature. So this is the right size piece of equipment. This piece of equipment here has a very low load cycling zone, but does need that supplemental heat at temperatures below 24 degrees, we said. 24 degrees, yes. So this is our undersized piece of equipment. Here we have everything, all the product information that was seen on the product pages laid out in columns here that we can easily compare between the three. We compare efficiencies, see which AHRI number each one is, and see your your product size and preheating information down here. So say I want to see, okay, my capacity balance point is 8 degrees, 24 degrees, and -6. Let's look at the one that's 8 degrees. I want to pull that one up on the graph. I'm not sure which one it is. I don't want to cycle through the graph. So you have 5 up here. You can simply click show graph and it'll pop over to that thing right here. If you want to go to that product page and say, I want to, okay, this is the piece of equipment that I'm selecting, you can simply click on the AHRI number, which has the little link. That's the same link for the product page. Click it, and it will pop up with your product page information here. You'll have to enter in your advanced data system sizing information again, but that simply clicks right to your piece of equipment you want to select. If you want to pop out any of these graphs to its own page, you can simply click this little export button. That'll pop it up in its own window with just the graph. That might be bigger and easier to look at. I'm going to look at, real quick, some other features of this specific heat pump here. Just to go over what the more simplistic view of it is, which is what we call basic view. So if you are to click basic view up here, you'll notice that this graph down here changes. And you can still add in and remove features, but it removes a lot of the background information. It just kind of paints a more simplistic picture that might be easier to explain to a homeowner or hand to a homeowner for them to understand. It doesn't have all the product sizing for heating and product sizing for cooling information, but it does paint a pretty good picture on how well that heat pump is going to operate without providing too much information. To return to that classic view, you can better interact with the graph. Simply go up here and click classic view. And it will repopulate the graph with all the information, and it will have product sizing for heating and product sizing for cooling tables down here. While we're here, I'm going to look through the optional settings and look through what we've already done is the apply compressor lockout temperature that might be useful for that undersized piece of equipment. And then we've already looked at that for a dual fuel system. So if you're sizing a heat pump for cooling and then having dual fuel system, this is a great use of the lockout temperature. The D-rate percentage affects the annual load that is seen by the piece that is seen at that location. It is meant to account for some solar heat gain of that home and zone. The default value of this is 10. So if you were to enter 10 in here, these values should not change. If you want to increase that, say you have a home that has a lot of glazing, maybe it's west facing and gets a lot of heat from the sun. So in these temperatures that are 40 degrees, but you get some nice sunny afternoons, you can up that D-rate percentage to whatever you like. If you enter in 15, 150, 15, and then hit run system sizing. It will recalculate all your information down here, as if that annual load seen by the heat pump is 15% less than what is just interpolated from 60 and the heating design temperature. But we are going to return that to 10 to return that to original values. And then optional is to manually set the load temperature capacity rating. So say I was in an area that had a heating design temperature of 0. And we can see that this specific heat pump is only tested to 5 degrees. That's what NEEP requires. There are some heat pumps that are further tested into the negatives, which will have a data point down here in the performance specs for a different temperature below 5 degrees. That'll have minimum and maximum capacities and efficiencies. However, this piece of equipment is only tested to 5 degrees. If I was in an area that had a heating design temperature of 0 degrees, I know that this heat pump really doesn't just turn off at 5 degrees because it was tested to that. If it hits 4 degrees outside, the heat pump doesn't just short circuit and stop working. It does work, and it typically will take a similar line to what this heating maximum capacity is at, maybe a little steeper. It should degrade about in a similar pattern to what it is going there. So if I look at this here, this heating maximum capacity line, as it gets to 0, is probably somewhere around 10,000. So I'm going to hit 0, and I'm going to go with 9,500. So I'm going to be a little conservative on that, and hit run system sizing. And that will extend my modulating zone to that 0 degrees. So if my design temperature was 0 degrees and I was looking for some more information in the product sizing for heating information down here, I would simply enter that in here. We don't manually, the tool doesn't automatically extrapolate from the maximum and minimum capacities, just because we don't want to assume anything that the manufacturers haven't reported. If you're looking for some more information on your specific project, we trust that you have the know-with-all and the ability to do so, and then hold that liability to yourself. So that's how you use the set load temperature capacity rating, and that's what you would need to do if you have a heating design temperature below what is tested. I'm going to pause there. Tara, are there any other questions about these, maybe the compare products or these specific features?
So some of them are more broad. Do you want me to save those for
We can
later?
save those for after, yeah. So all I have left is the stack features product.
Let's go through that and then we'll hit all the questions we can.
Sounds good. All right, so back to the list view. I'm going to clear my list, and I'm going to take a look at what we've already looked at. So we've looked at the oversized, we've looked at the undersized, we've looked at the right size. The problem with the oversized is it has low load cycling. The problem with the undersized, if it doesn't have it doesn't have the maximum heating capacity needed to meet that design load at the design temperature of 8 degrees. However, maybe we wanted to install 2 of these systems, one in the living room, one in the bedroom, to meet the heating needs of the home and also keep those minimum capacities low. So what I'm going to do, and you can add multiple systems of multiple manufacturers or multiple within one and use the stack products feature. What I'm going to do is, to keep this simple, is to select 2 of the same pieces of equipment that we already know is 57.7% of the design load served, but has a very low minimum capacity and can dehumidify the space really well. So I'm going to add 2 of these in here. You can see my count is 2. If I wanted to reduce that to 1, I'd simply click the green minus sign. And I'm going to hit stack products. And what that's going to do is create a new product sizing for heating page that will stack these 2 products together as if you're building a multiple compressor system. If you're installing one of these in the living room and one of these in the bedroom of this small 1-bedroom, 1-bath place that has a heating design load of 12,500 BTUs at 8 degrees Fahrenheit, how does this system operate? And we can tell it from here by comparing from what we've seen in our oversized, undersized, and right-sized pieces of equipment, that these 2 systems working together can meet the needs of the space at 8 degrees Fahrenheit. The maximum capacity of both of these systems working together is greater than the load needed for the space. That's fantastic. But then you look over here and you can see that the single system low load cycling is only 50 degrees and above. You can add in the total system minimum capacity and the modulating single system to show this area, which is depending on how the system is set up, the area that the degrees Fahrenheit outside, that the systems might cycle on and off. One of the systems might cycle on and off, and the other system might take primacy. If they were operating in complete separate zones, you don't want to look at this specific visualization because the heat pumps won't have interaction to each other. However, if this is a single one bedroom, one bath apartment, and one heat pump head is in the living room, one heat pump head is in the bedroom, all you need to do is open the bedroom door and air will flow kind of back and forth between the two rooms. You can look at these two systems together as if in those really low load hours, one heat pump head will turn off and give primacy to the other heat pump head that will operate at its minimum and really low speeds and provide heating to the space, the little amount of heating that the space is needed, while the other heat pump should remain off. The benefit of that is you don't get systems low load cycling. If you had a larger minimum capacity, the system low load cycling is probably going to be at a higher degrees Fahrenheit or a lower degrees Fahrenheit, excuse me, and opposite for cooling. So this heat pump primacy zone, one heat pump in the same zone should give primacy to the other pieces of equipment, and it should not click on while the other one clicks on and operates in its low speeds for that time. So the benefits of adding two systems like this in a single space, you get low load cycling zone, but you get to add the maximum capacities together because they will work in unison together when the load is higher than one system to meet the needs of the space. I do want to reiterate that these systems should be operating in a same or similar zone that they will interact with each other. We don't want to be looking at, in a ranch style home, if you have a heat pump on the complete one side of the house and a heat pump on the other side of the home, another wing of the home, where there's no interaction and no airflow between the two of them. We don't want those systems to be stacked together and to account that they will, give primacy to the other because they're both independently heating and cooling their own zones. So we only want to look at multiple systems. You can look at multiple system maximum capacities for those systems that are meeting the whole needs of the whole home. Well, we don't want to take into account that low load cycling. If they're each going to be independently responsible for their own zones and have no interaction between the two. Tara, do we have any questions coming in on the stack systems?
I don't believe we have. Oh, yes. Okay. Can you have a centrally ducted system and a ductless system operating together? Head in the family room, for instance.
Yes, you can. Is this, I'll take it as both. Within the tool, you can add in, as I said, you can go and do the search. And then you can come up here and say, I also have a single zone centrally ducted Bosch unit. And then add in a Bosch unit we don't have. Let's go with a compact unit. And you can add these two together and then stack these two products together within the tool. This is what those two products. So this one is a ducted system, and this one is a ductless system. They can interact well together within the tool. And I know that is a common layout in real world scenarios where you have a ducted system that maybe it doesn't, the existing ducts that were originally used for the furnace do a great job of distributing heating and cooling to the first floor, but maybe those second floor bedrooms don't get enough heating and cooling. There's not enough airflow between them. So what an installer will do, we'll install ductless systems in the upstairs bedrooms, and then keep that ducted system in the downstairs room. Or maybe just supplement some rooms that do have duct flow to them and interact with the other spaces, but don't necessarily get air mixing and enough air to them.
Thanks, Parker. And also Bruce put a great question that was more of a note in the chat that I wanted to flag. We should really remind people that this is not a tool for proper sizing of equipment. It's a guide to qualify various options. Final sizing and selection must always be based on looking up capacities at the design temperatures in the manufacturer's performance table data. And it should always start with a proper load calculation as well.
Correct, yes. Yes, I would absolutely agree with that. This is a visualization tool to help assess how well a heat pump is going to operate over the course of a year. It's not actually used, it shouldn't actually be used for sizing. You should refer to your sizing resources for that.
Thanks. So what is the recommendation for when a mini split indoor unit is too large based on the heat load, but the manufacturer doesn't make a smaller size?
Good question. This comes up frequently if you have like smaller kids' bedrooms, and the smallest size of a heat pump, ductless heat pump head is 9,000 BTUs. It's very rare that you get a small kid's bedroom that has a 9,000 BTU heating load. Um, it's currently a kind of out there question in industry, depending on who you ask. I think a good solution of it is adding like a compact ducted system and splitting the load of that compact ducted system between multiple rooms, maybe splitting the load between that bedroom and a bathroom or a bedroom and adjacent bedroom. Compact ducts allow for, short duct runs, and fitting in small spaces like above closets and crawl spaces, etc. And they can also be concealed well, whereas that's often heard from homeowners a complaint is the look of a ductless system, and the wall space that it takes up. Whereas a small compact ducted system, you could split the load between multiple rooms, and do it that way. I do know that that's a problem that's trying to be addressed in multiple ways, and will hopefully be widely solved soon.
Thanks. Dean wants to know, can we move the load line from 60 Fahrenheit to a thermostat setting, say 72?
We don't currently have the ability to do that. That might be something that can be added in future iterations of the tool. So what Dean is asking is this temperature right here, so this essentially zero load point at 60 degrees. Why this is 60 and not a temperature load, a 72 degrees temperature set point, is the load at those times where it's 65 to 70 are typically almost zero. Typically the sun will account for that load, and your heat pump won't operate during those times, just to bring the indoor temperature up to 72. You'll have enough internal load from the home, and external load from the sun, external heat from the sun, to bring that heat pump up to a comfortable indoor temperature. We've considered adjusting that or allowing a user to adjust that in the past, and it's just lost out to some of the other upgrades we've had.
Great. And is there any rule of thumb for low load cycling percentage and supplemental heat percentage, something that people should be aiming for?
No, there's no real rule of thumb. What you really want to do is make sure that if you do have supplemental heat and it's small, it shouldn't be an issue. You obviously want to use your sizing resources outside of this visualization tool to make sure that that heat pump is going to be able to keep the space comfortable. So use your ACA and ASHRAE materials to size your equipment. To visualize the low load cycling here, I think an important factor is using the annual load hours. If your low load cycling is encapsulating a large amount or a large portion of this big blue histogram behind it, or maybe some peaks, then you're going to be low load cycling through a large amount of the year. And another piece of equipment that has a lower minimum capacity might fit that space better, and not low load cycle for as many BTUs as is needed in that space.
Great, thank you. So trying to find one that we can answer in time. If I look up the capacity at design temperature and it's higher than the lowest NEEP listed value, can I enter that as the low temp capacity rating? And will it override the interpolated values from the listing?
Can you ask the beginning of that again?
Yeah, if I look up the capacity at design temp and it's higher than the lowest NEEP listed value, can I enter that as the low temp capacity rating, and will it override the interpolated values from the listing?
So are they asking if they enter in a low temperature capacity rating? So the low temperature capacity rating, it should take, if you are they asking if they enter in like 5 degrees, if it's going to be more than what is currently listed down here as the maximum of 5 degrees?
I think an example would be if the design temperature is at 5, but the lowest NEEP listed value is -22. Um, would would entering that value at the lowest temp capacity rating override the interpolated values?
Um, so entering, I will say that if these values are incorrect from what you're seeing as a manufacturer from the manufacturers, reach out to someone within NEEP because these values should be the actual performance specs uploaded and updated by the manufacturer. If they're different from what you're seeing that the manufacturers show elsewhere, it might just be an error somewhere along the process. Um, if you were to enter it in here. So I'm honestly not sure. I haven't considered that because with all the data checks we do to make sure things are correct, I hope they're not seeing that. So if you are seeing that, please reach out to NEEP or myself or your manufacturer, so that can be corrected within the tool. If I don't know if I'm answering that correct or not.
Thank you. I think good answer. And if there's still that question, maybe phrased in a different way, feel free to email us about that. Okay, so I'm seeing we only have 3 minutes left, so maybe we'll switch back over to slides just for a quick wrap up. And please do reach out, everyone, with these questions. I know there are tons of them, and they're all really great and would be useful to share out. So we'll try our best to get answers to you. All right. Thank you, Parker. So just to sum it up, first of all, thank you all for joining, and thanks, Parker, for running us through that tutorial. Um, Oversizing is a common issue that programs are trying to avoid, and our tools are meant to help users select products that are sized to best match the design and annual heating needs of the space. And so this tutorial is going to live on our website to help you navigate the tools in the future. And programs and contractors can use these tools to support best practices. And if there's any questions or you want to see new features in the tool, NEEP is here to help. So always reach out. Next slide, please. And there were a couple questions on what's next. As a quick preview, we'll have some short form video tutorials coming out soon with the help of TRC again. And we'll be adding a refrigerant filter onto the site as heat pumps with A2L refrigerants are coming on the market. With the upcoming refrigerant phase down, we'll be able to search between the units with the refrigerant that you're looking for. And we're working on continual data quality improvements to make sure that this data is accurate and robust, and the market can continue using this for system sizing and selection. I think there was a question about air to water, and we mostly are aligning with others in the market that are creating specs for this. We don't want to create a competing spec. We want the market to be aligned. So there may be a chance for air to water units coming on the list, but we likely won't be developing a cold climate spec for that. I believe Energy Star is working on that, and maybe some others too. Thank you. Next slide. And don't forget that our NEEP Summit is this year, June 11th through 13th in Weehawken, New Jersey. We hope to see you there. Registration's live on our site, so sign up when you can. Next slide. Thank you all for joining, and thanks, Parker. once again, our contact information is on this slide, and these slides and recording will be sent out to all of you. So thank you very much, and I hope you have a great rest of your day.